Welcome to breadboarding. This is video 22 in the Nanocomp 6809 breadboard computer series. So in this video, I'm going to be looking at fixing the snow on the video outputs, and this is caused by the CPU accessing the video RAM whilst it's being used for the display. In the previous videos, which I've covered over the whole series, we developed a video controller card that has a character mode that is based at 30 lines times 80 characters with 16 colours, and we developed a Tetris game to run on that. Then did a high-res graphic mode, so 640 by 480, and that just has two colours, a Lunar lander game there. And then finally we did the high colour graphics, 320 by 200 pixels with 256 colours, and that uses a 262,000 colour palette compatible with VGA, and for that we just showed the Doom title screen. So what I'm first going to do is going to cover the high-level design of the character mode, the high-res graphic mode and the high-colour graphics mode, so that when we go in to look at how to fix the snow, it sort of kind of makes sense. If you want to see how these were developed in detail, then the video controller series will take you all the way through from the very beginning to the end of the high-colour graphic mode. So this is the VGA character mode. The memory map is down the right hand side here, and I allocated a 16K region to the video RAM, and that's known as the Y0 address select on the chip enable there. But we also had the character RAM, so for the character generator was at C000. The way how this video display works, it makes use of a VGA compatible 25 MHz dot clock. We use the CRTC controller chip, cathode ray tube controller, CRTC, and this is a Motorola 6845 compatible device, but in fact it's a Hitachi HD68A 45S. And this is quite important because the A means that this is actually able to run a bit faster than the default 4 MHz clock that the original Motorola chip was running at, and the S also means that it's capable of running at higher clock frequencies. In particular, the character clock frequency can work at VGA speeds, whereas the default 6845 would not be capable of running at VGA speeds. So what happens here is the CRTC produces the video horizontal sync and vertical sync signals, and also provides a display enable signal as well, which blanks out display during the synchronization vertical horizontal sync periods. We have the CPU address bus down the bottom here and the CPU data bus. So CPU addresses are CA and the CRTC addresses are known as MA. So what the CRTC controller does is provides addresses through these buffers to two video RAM chips. Now in the character-based mode, we're only using the bottom 8K of each of these chips. The video RAM 1 does the characters and the video RAM 2 does the colours or attributes for each character. When the CPU wants to update these video RAM chips, then what happens is that the address bus here is routed through here to the video RAM chips, and then the data is then accessed through the following chips this way. The way how the characters are generated is the CRTC produces a raster address or RA lines, and what this does is allows the character generator ROM or RAM in this particular case, which means the characters can be software definable. What this does is outputs from the chosen character an 8-bit value that chooses address lines 4 to 11 on the character generator RAM, but then the bottom A0 to A3 are chosen by the row of the current character that's selected. So what this means is that as the character is drawn, it does each individual line of dots for the character. And these two latches, one saves the current selected colour and makes it available over on the right hand side here for use. We can have 16 foreground and 16 background colours, so 4 bits for each. And then the output of the dots necessary for each character, so for each row there's 8 dots that would come out of here, and that gets fed into this shift register, and then as the shift register is loaded, and then the dot clock then rotates the output of those bits, and those provide a foreground background signal. So when it's 1 it means show the foreground, when it's a 0 show the background. This program or logic device here does a lot of the video control signals in this first version, and what this also then does is feeds this multiplexer to decide whether or not we're going to show the foreground colour or the background colour. display enable will suppress the output to the monitor during the various blanking periods. And then the digital analog converter that we used in the early stages here was very simple. It's basically a buffer with a number of resistors to provide the signals that are necessary to feed the VGA monitor. So it needs to produce a voltage between 0 and 0.7 volts for full intensity for the red, green, blue signals going output there. So that was the character mode. And then what they went on to do is to develop this to actually add a high resolution 2-color graphics mode. So what I've done here is I've highlighted the new chips we added in purple here, and where there are bits of the design which were used for character mode, these are just shown in grey so we don't actually get confused here. What we're doing here is, rather than the video RAM 1 and video RAM 2 controlling the characters and the colours, then the 8-bit data that we're sending out to the display either comes from video RAM 1 or video RAM 2, depending on the address range, which is currently selected. And then the output data feeds these two new latches. The way how we take the address lines out of the CRTC chip and feed it into the video RAM needs to be a bit different here, in that we need to be able to show 480 lines on the screen, but the CRTC chip is only capable of going up to about 127. And so the way how we address this is by using 60 character rows, but then each character row then has the 8 raster lines that we saw for the character generator RAM. So in fact, now what we're doing is we're making use of not only the memory address from the CRTC, but also the raster address lines are helping to generate the signals necessary to access the video RAM. Then we also need to add a page register, because we've now got 64K of RAM, but we only have a 16K slot for accessing the video RAM using the Y0 memory select signal. And so we added a page register that allows us to switch between the 4 video pages via the PA1 and PA0 values in here. So that basically allows us to select which of the 16K blocks of the video RAM we're accessing. And these Y0 signals up here, when the Y0 select signal is 0, it means the CPU is accessing the RAM, and when it's 1, then it means the CRTC is accessing the RAM. And you'll see that the way how some of these buffers and things work and select things, and these bidirectional buffers here all work in a similar way. Now these latches here are controlled by a variety of signals coming from the video PLDs. We needed to add another PLD here to extend the number of signals that we were having. And the only other thing here is you also needed to add the ability to be able to set the color values in this particular latch here directly from the CPU bus. And what this allows us to do is to say we want the foreground and background colors for this mode to be defined from any of the 16 basic colors we have. So it doesn't have to be white and black, it could be green and red if we wanted to. So then if we look at where the data is coming from, so the 8-bit foreground, background values are coming out of each of these latches, going to the shift register, and then determining whether we show the foreground or background colors, much like we did with the character generator output. So that was then using the same video digital analog converter that we used before. So then we went on to extend this then to do the high color graphics. So in the high color graphics, again, I've added the changes that are in purple, and the high res graphics is shown in blue, the character based is shown in grey, and where certain bits are used by both the high res and the character graphics, then they're kind of in the half grey, half blue color. In order to do 320 pixels across the screen, the CRTC can only work up to about 3.7 megahertz for the character clock, so we couldn't really increase the number of character cells across the screen. So what we did instead is break each character cell down into 4 pixels. And we did this by taking the QC and QB clock signals, and this comes from dividing the 25 megahertz dot clock. QB I think is divided by 4, and QC I think is divided by 8, and is also what the character clock is. So by using these 2 signals, clock signals, to provide the address information for the individual pixels, we're able to access the RAM quickly enough to be able to use 8 bits for each individual pixel. And these new latches that we added here basically take the output of the video RAM. This latch here is reused, and this new latch down here is used to actually send the 256 colour pixel information. So what happens, depending on which range of the memory is selected, then the data in this latch will be sent to this foreground background multiplexer. This multiplexer needed to be made more complicated because it needs to take either all 8 bits of the data to send out to the digital analog converter if it's in graphics mode, but if it was in high-res graphics mode or in character mode, then it would actually use the 16 foreground, 16 background colors, so it would actually separate the 8 bits down into foreground and background. And so this multiplexer needed to know whether or not it was running in high color mode or if it was running in character or high res graphics mode, in which case the foreground background value would then switch between the upper and the lower 4-bit color values. And the other thing we did in this mode as well, we added a video digital analog converter. So this particular chip is a VGA compatible chip, and what that allows you to do is define up to 256 individual color values out of a palette of 262,000 colors, and that allows 6 bits for each color to be specified in the palette register. And we'll see when we look at the Doom startup image that the portable network graphic files which that comes from contains the palette information specific to that particular image. So it's quite a complicated configuration. This is capable of producing close to what the VGA standard was able to produce. I did actually come across a little known video standard known as MCGA, which only I think was introduced in the IBM PS2 Model 30 and didn't last for very long, but it's quite interesting in that that was an extended version of CGA which had these two high color modes and the high-res graphics modes are very, very similar to what we've been able to develop here. So in future videos, what I may do in looking at Intel platforms will perhaps try and build the video controller into something compatible both with CGA and the MCGA standard. Now, when we come to look at the snow can be caused generally by the CPU accessing the video RAM whilst the CRTC is using the video RAM to output data to the display here. Now, there are a number of ways of avoiding this. One is that we can check the display enable signal, which goes low during periods of the horizontal and vertical sync. Horizontal sync is only about 6 or 7 microseconds, so there's not very much time to do anything during a horizontal sync pulse. Vertical sync will be up to about 10% of the overall video frame period. So at 60 Hertz, where each frame is about 16 milliseconds, you get about 1.6 milliseconds between the frames. And at 70 Hertz, which I think is about 14 milliseconds, you get about 1.5 milliseconds between the frames. So you get about 10% of the overall display period available during the blanking periods to be able to do the update. So you have to sort of fit a lot in that period of time. The cause of the snow is that the CPU is accessing the data here. And so if any of these latches try and load any data during the CPU access, then it is quite likely to be wrong. And also during the time that the video RAM is being accessed by a CPU, then the data address is actually coming from the CPU and not coming from the video controller chip here. So this is the primary cause of where we get this interference, and obviously the faster that the CPU is accessing the video RAM, then the more likely that this is actually going to see interference. So what we're going to try and do is to look at how we can reduce this. I don't think we're going to be able to completely eliminate it, but we hopefully should be able to reduce this. So in order to, what we're going to look at in this video is, I'm first of all just going to go through and test the video controller mode. So I'm going to be showing the character-based mode using Tetris. I'm then going to show the high-res 2-color graphics using the Lunar Lander game that we produced in some of the earlier videos. And then finally we'll look at the high-color graphics loading the Doom title screen image. For each of those, I'm going to use the logic analyzer to record many of the signals for all of these modes, and then we can look later to see how those signals perhaps have changed. We'll then try and fix the snow, then we'll test all the various video modes again, and then we'll look at certain logic analyzer signals to see where the changes were. So as I said already, to fix, there are a number of ways how we can eliminate the snow. So probably the simplest one, and the one which I think was advised by IBM for the original CGA adapter, is do a software check for the vertical sync display blanking periods. So as I said, at 70 Hertz, this is about 1.5 milliseconds every 14 milliseconds or so. And the Tetris version 2 game that we'll be looking at used this sort of video blanking waiting on the 60 Hertz display. It wasn't perfect in that there were one or two operations which probably took longer than the sort of 1.6 milliseconds, but I didn't spend too long trying to tune that blanking, video blanking. The other way how you could do it is by using dual port video RAM. Now, in the very early versions of the video card, I did use these 4K by 8 bits IDT 7134 chips. Now, these are quite large 48-pin chips, but in order to do the 64K of RAM, these have now gone up to about £15 each. I don't think they're produced anymore, so they've now become obsolete. So in order to do the 16 4K chips we'd need, quite apart from the amount of space on the breadboard, I'd also need to spend £240, almost probably $300 on these RAM chips, which I didn't think was a particularly good solution. So number 3 is the first thing that we're going to look at. So in some of the previous videos, what we've done is upgraded the CPU clock from 4 megahertz to 8 megahertz. Now, because we're using the chips which are capable of running at this faster frequency, what we can now do is perhaps to run the CPU off a clock which is sort of synchronized to the video card. So the video VGA uses a 25 megahertz dot clock. If we divide that by 4, we'll get about a 6.2 megahertz clock. And if we use the CPU to run off this clock rather than this one, then what should happen is the CPU memory axis should be maintained in time with the video access. So if we can just adjust the phase of that 6.2 megahertz clock for the video access and the CPU access, then we should be able to get the two signals to kind of interlace in a way that reduces, if not completely eliminates, the video interference. There is another option that we've got. There is a memory ready feature on the 6809 and in the 6809E that we used for the 8 megahertz version. There is a circuit that allows us to introduce a delay to the memory access, and what we could do here, if number 3 wasn't sufficient, we might be able to add this delay circuit to the clock, and that would allow us to extend the CPU access to the video RAM perhaps until a point in time where the CRTC had finished with it, and then we could let the CPU access it. We do have a slight problem here with the 256 high color mode in that each pixel is actually running at about 12.5 megahertz. So this means that each pixel is only spending about 79 nanoseconds per pixel. Even with the 8 megahertz CPU, the signal that we get out for accessing the video RAM is 160 nanoseconds wide. So really, we would have to do something very significant to try and get this high color mode to work and interlace with the CPU. I really don't think it's going to be very easy to do that. So I was thinking about this, and there might be a couple of ways of doing this. However, I'm not sure they're going to be that practical. Because we have 2 banks of video RAM, we're only actually accessing 1 bank of video RAM for half the time on the screen. So I did think that what we could do is use one of the address lines that switches between the video RAM 1 and video RAM 2, and that would actually give us about half a frame, so 7 milliseconds for every 14 milliseconds, where we could update the video RAM chip. Unfortunately, obviously, the other video RAM chip still needs to be able to talk to the CRTC at that time, so it would require us to have the CPU addresses multiplex per video RAM chip so that one could be talked to by the CPU whilst the other was being talked to by the CRTC. So I think that would be very, very messy. If we're using a very large scale integration chips that such was used in the VGA standard, then that might be an option. However, because we're using standard DIP chips for doing all of this stuff, we're not using any sort of higher density surface mount type chips, we're probably limited on what we can do there. What we're going to do now is to go through and look at the current video modes using the Tetris, Lunar Lander and the Doom title screen image. And then what I'm going to do is to have a look at changing the CPU clock, and then we'll see whether or not that improves our character and high res graphics mode. I wouldn't expect it to make much difference to the 256 color mode, but we could then actually have a look then and see if there may be other options here. One thing I was thinking is I might be able to do the vertical sync display blanking, so as we load the data into the video RAM, we might actually be able to make use of that and see if that makes it any better. So this is the default Nanocomp startup screen, so it's just running the built-in monitor here. You can see this is the default video mode, which I think is 80 columns across by 30 down. Now you may just about be able to see there is very slight interference. I don't believe this is caused by CPU updating. I want to look into this as we go through this, but what I'm going to do first of all is to actually show you the logic analyzer and the signals that we're going to be looking at here. So for the moment you can see there's a flashing cursor at the top here, and we've just got this text here. So this will be in white, which I think will be color of 0F, and the background here is blue, which I think is 02. So when we look at the data here, we should actually be able to see where this is occurring. So I'm just going to switch back to the desktop, and we're going to run up the logic analyzer. So I'm just going to run this, and it's just reading the current data that we see there. And what we can see here is the data I've currently got connected to the input to the video digital analog converter. So this is effectively the values of the colors that it's actually selecting. We've also then got, if we drill down here, we can see that we've got the 25 megahertz clock, and then these are the divider. This is divide by 2, divide by 4, divide by 8, and this also happens to be the character clock. There also, when we did the 256 color, we actually had some of these clock signals delayed slightly. So these are these signals. Then we've got the Y0 signal for when we're accessing the video RAM. Display enable. What this shows is when the video signal has been output to the monitor. So when it's high, it means we're outputting the signal. And when it's low here, then it basically means that we're not doing anything. And if we zoom all the way out, what we should be able to see down the bottom here, we've got the vertical sync and horizontal sync. So you can see here, this is at the end of the page, at the start of the page, and then down here, this is each horizontal line. And then during this period, you can see that display enable around the page end and the page beginning is disabled. And then for each line, display enable is showing most of the line. And then during the flyback period from the old CRT monitors would have an amount of time to allow the electron beam to go back to the beginning of the line. And that's this period here. Now this is fairly short. There's not a lot of time at the end of each line. We've only got about 6 microseconds, which is not really much for the CPU to do very much. Whereas when we actually look at the period here, this period here is something like 1.6 milliseconds. So there's a bit more time available to do something in this period of time. And the actual period of the whole page is about 16.4 milliseconds. So each page is about 16.4 milliseconds, which is about 60 hertz. So one of the things that we did do with the Tetris game is we actually checked to see when the display enable signal was low, and we only did updates for the majority of the code during those blanking periods. Occasionally you did run into periods of time where an update would take too long and would actually start interfering here, but hopefully we'll be able to actually resolve that with these changes. And these are all the other various latches and things that we'll be looking at. So these are all the character latches used for both the character mode and the high res graphics mode. The G1 and G2 latches are actually used mainly for the color mode, but in the character and high res graphics mode, the G2 latch mirrors pretty much the character latch there. So these are all the signals that we need to coordinate, and obviously as we start to update the video, then we have to really coordinate when these latch signals and things are actually interlacing with the memory write signals in here. But this value here is just what we get on the default screen. We're not doing any updates to the screen at this point in time, so this is just our default starting point. So I'm going to save this And as I go through showing you all the other video modes, I'm going to be saving these captures as well, so that I've actually got some data to go back to when we've actually made changes, so we can actually go back and see how the old signals were working and how the new signals are working. So I've saved that. Now what we're going to do is to go down and send our first code. So what I've got here is a terminal emulator, and we're going to look at the Tetris software first. Now I've got two versions of this. The first version didn't have any optimization for using the video blanking period, so this probably is going to be the messiest. Then we've got the version 2 that had some enhancements and only updated the screen most of the time during the video blanking period. And then this version has the delays taken out, so this shows how fast it can go at the maximum gravity speed. So we're just going to download this particular one first. So I've started the Nanocomp and I'm just going to send the file down. I'm not going to show this process for every one of the test programs because it will get a bit dull switching backwards and forwards. So I've loaded that. We'll just switch back to the VGA capture card. So I'm just going to run up our initial Tetris game. Now you can see there's quite noticeable snow there on the screen. So as I move the thing around, it's a bit sort of sluggish, and you can see there's very, very clear amounts of snow from the video updating. If we just try and drop a few things there. Okay, so you can see that that's not great. So what I'm just going to do is to run that again. And whilst that's updating, I'm just actually going to capture another set of all the signals. That saved Tetris 1. So we'll abort that then. And what I'm going to do now is just download the next version of that. So this is version 2. This had the random number generator seed based on when we pressed S for start. So each time we should get different tetronymos coming down. So fast that the key polling sometimes can be a bit too fast. It needs to be modified. Okay, so you can see here, this is better. You can see there's much less interference. Occasionally you do get the odd bit of interference. I think when the bottom line is hit, it sometimes results in some interference. But generally we were trying to make sure that we're only updating the screen during the blanking periods. So that was better. So I'm just going to record that. So I bought that. Now I'm going to download the fast one. So this has the delays taken out. So this is the fastest that it would actually work. So if you got to the highest level, and this is the highest speed it's able to run at. Okay, so we'll press start again, and you'll see when this comes down, it's way faster. And we do get a little bit more screen interference because of the speed that it's running at. So I've also captured that one as well. So that's the character mode. So we've already done a little bit of software changes to eliminate some of the snow, and it's certainly a lot better than the first version, but there's some room for improvement. So just reset that back. Now what I'm going to do is to load the Lunar Lander game. So the Lunar Lander game also has some custom fonts, so you might see some of the fonts at the top of the screen there may change as it loads the custom fonts. So I'm just loading down the Lander game. And you can see there the fonts have now been loaded because they've changed some of the fonts up there, only really the uppercase. So now let's run up the Lunar Lander. And there we go, there's the Lunar Lander. You can see that the little bit of snow effect there is not as bad as the first version of Tetris, but obviously there is some scope for improvement there. I'll just wait for it to go to the expanded screen. You can see there's definitely quite a bit of snow there. So hopefully that should give us some ability to improve that there. I'm just going to capture the logic analyzer data. So I'm just going to reset this back now. Now, in order to load the Doom image, which is the 256 colour graphics, I do need to download a sample program and the palette information for this first. So I'm just going to switch back. So I've put the Nanocomp into load mode. And what we need to do is to, first of all, I've separated out the palette information. So we send down the palette information from the PNG files. So the portable network graphic files include the palette, a dedicated palette for that particular file. So I've downloaded a palette. Now I need to send the test program down here, and that loads that palette information into the video DAC. So we're just downloading that. And then we just need to run that, and once that's run, what it actually does is loads the palette information in, and then finally we can now send the actual image. So when I send this, what we should be able to do is to see this loading in real time on the capture card. So let's just switch back to the VGA capture card. Okay, so it is blank at the moment, ready for this because it's already in the graphics mode. And if I now start sending that, and you can see as the screen's updating, you can see that sort of red snow appearing in the top half there. We're not seeing anything in the lower half because that's the separate video RAM. So it's now in the second half of the video RAM. You can still see there's some interference in the top there. As I said earlier, the challenge here is that the pixels here are updating at 12 megahertz, so there's no way I can interlace the CPU access with this particular mode. Okay, so all I'm going to do is to reload that, and then I'm going to capture the information on the logic analyzer, and then we're going to have a look at how we can change the CPU clock to work off the video clock. Okay, so that's now completed, and I've got the capture of that as well. For graphics mode 3, the high color mode, I originally thought I might have been able to do something with the hardware. Unfortunately, as I thought about a bit more, it wasn't really possible to do this. We would need to add a lot more multiplexers to the video RAM chips to be able to use this particular mechanism I originally thought about. But what I did think about was saying, well, could I use the software check for the vertical sync display blanking, and would that actually improve things? So what I'm going to show you now is 2 test programs I've done to show how that might work. So the first one is my serial SREC test program, and this basically used some of the SREC code that I developed for reading the SRecord file off the hard disk in one of the earlier videos. And all this basically does is does some of the palette initialization, initializes serial port, switches into graphics mode 3, and then starts reading the SRecord file. And as it goes through, it updates the memory, and then once it's done that, it then will load the palette information that we've looked at before. So the Doom PNG file color palette is loaded at 4000 hex, and all this bit of code at the end here just updates the video palette so that it actually looks okay. So what I'm just going to do is to switch over to Nanocomp. I'm going to load that particular program, and we're going to show what that looks like. And we would expect here to see the snow video interference because we're not doing anything to do with accessing the video RAM. So I'm just going to load the test program down onto Nanocomp. This is our serial SREC. Okay, so that's completed. So I'm just going to run this up. And what this is going to do is going to clear the screen, and now it's just waiting for me to send it the Doom SRecord file. So I'm just going to download the Doom SRecord file, and we should see that it will start to update. So you can see as the screen's updating that there is some interference on the screen as we're updating the video RAM. So we'll just let this run through to complete. Okay, so once it's set the color palette correctly, then you can see that it's loaded our Doom image, and that's a pretty reasonable rendition of it. So what I'm going to do now is to go back and look at a modified version of that serial S record program, and what we're going to do is to look at whether or not we can only update the screen when we're in video blanking periods. And what I'll show you is a capture of the logic analyzer that shows you where we're actually doing the updates. So test program is very similar. Apart from now, we're doing our wait for screen blank initialization, and this just sets the various peripheral interface adapter ports and things ready for us to be able to check the display enable signal, which is on, I think, bit 7 of one of the port B, I think, of the peripheral interface adapter. The code in the S record file is very similar. Apart from what I've done now is I've actually split out the reading of the data from the serial port, then I'm putting that into a buffer array, and then once I've got a whole line of data ready to write to the video RAM, I'm then waiting for a screen blank period, and then there is a fairly tight root loop here where we're taking the data in the buffer and we're outputting that. Now, when I was developing this, one of the things I did run into is issues with the serial ports, particularly with the CTS RTS signals, and it looks like, although I had set up the terminal emulator, which is sending the files to and from the Nanocomp, to use RTS CTS handshaking, that because of the way how the pins are set up on the USB serial adapter, that it doesn't appear to be working properly. So that took a little bit of time to get to the bottom of, but I think I have a working solution now. And so what I'll show you now is this modified version of the program, loading the S record file, and we should be able to see that we can actually update the screen without resulting in any snow. So just sending down the serial S record blanking, video blanking version of the program. I'm just going to switch over to the VGA capture card. So now I'll run up this version of the program. Now it's waiting for the S record file to be sent. Now what I did find is I needed to increase the, because of the serial communications handshaking issues, which I haven't fully resolved yet, there is an option on the sending of files to actually add a bit of a delay after each line, and I found that as long as I did that, I was able to coordinate the updating of the screen and avoid any issues with losing data coming across the serial port. So if I'm just going to select the S record file now, it does result in the data going down to the Nanocomp a little slower, but it does now update the screen without any snow or other artifacts. So I'm just going to let this speed up a little to get to the bottom. There we have it. So it was quite a bit slower, but it has now been able to update this display without causing any of the snow artifacts, which was really the primary thing we're trying to look at here. Obviously, what this does indicate is that updating high resolution graphics screens without having this sort of interference is quite a challenge, and really in later video cards then dual ported video RAM and much more sophisticated circuitry was used to actually avoid these sort of screen artifacts. So the high color mode is possible to get this working. If I had the serial communications handshaking working a bit better, we could probably get this working a bit faster, but I was really just trying to indicate how to stop the screen update snow. If we just have a look at the capture of that data. So this is the Kinkst logic analyzer output, and what we can see here is this is the period where we're updating the video RAM, and you can also see the display enable period here. This blank period here corresponds to the vertical sync blanking period. You can see here that this period, if we go here, we have a period of approximately This period is about 1.5 milliseconds, and the updates that we're doing here is taking probably about a third of that period of time. So it would be possible to tune this and get slightly more updates going on in the video blanking period, but it really starts to become a bit more tricky to coordinate all of the reading from the serial port and things. So what this indicates though is that by making sure we only do our updates, and this is the video read write and plus also the Y0 chip enables signal for the video RAM, then by making sure that that only occurs during the video blanking period here, then we avoid doing all of the mess on the screen. Well, I tried option number 3, changing the CPU clock to be the 6.2 megahertz, so by taking a direct feed off the QB clock divider, and it didn't really make any difference. And in fact, when I looked at it with Logic Analyzer, then the CPU cycle was then matching pretty much the CRTC cycle, and there wasn't really any scope for slotting the memory accesses in between those cycles. So even if I was going to change the CPU clock to be in step with the CRTC, we probably need to choose number 4 anyway, and if we're using number 4, then we probably don't need number 3, and we can leave the CPU running at a faster speed. So number 3 didn't really result in very much, so we're going to go on to number 4 now and look at how to sort out the memory access synchronization. So after running the various Tetris, Lambda and the Doom 256 colour image, I had a look at the captured Logic Analyzer traces, and really it was a little too complicated to try and work out what was going on. So I thought I'd write a much simpler test case. So this test program here actually goes through the 3 video modes we're looking at. So the character mode, the high-res black and white graphics mode, and then the high color mode. And basically what it does is a very simple test pattern. So in this particular case, we'll see what it does in a minute. Single red square, and then update the rest of the screen after that's been done, so we can actually see the same details, so we can see where the interference pattern occurs. Then similarly for the graphics mode 2, which is the black and white high-res color, all we're going to do there is to draw a line, an 8-bit wide line, again and again and again, and basically we're just polling for keys. So basically what happens here, the first part of the test, it will continuously update the screen whilst polling for a key. Once we press the key, it will then stop updating the screen, so we can then see what the static no video activity looks like, and then press the key again and it will go on to the next test. And then finally, for the graphics mode 3, what it's going to show is alternating blue and white pixels on 2 lines, and then we're going to update that data, and we should be able to see a much simpler interference effect. And when I've recorded those using Logic Analyzer, I'll then show you the output of those traces and analysis I've done to try and work out how to resolve these timing issues. So I've downloaded the test program down onto the Nanocomp, and if we switch over to the VGA screen capture, so I'm just going to run up this test program. So you can see here at the moment we've got a single, it's basically a red space and nothing else on the screen, but then because we can keep on overwriting that single red space again and again, you can see there an interference pattern that indicates where we're getting this sort of snow that we're trying to resolve. And if I press the I key, you can now see that when there's no video updating of the video RAM, then we don't get any of that interference pattern. And then let's go on to graphics mode 2. So you can see at the top there is the line at the very top of the screen, and then the interference we see there is the result in updating the screen continuously in a very tight loop. If we now press the key, so that stops it, so you can see that we've only got the single line at the top there when we're not doing any video updating activity. And if we go on to the high color screen, so you can see there that we've got our white and blue boxes at the top there, and you can see the interference that we get there. Interestingly, it's only on the top of video RAM that we get that, and then when I press the I again, then that stops. So what I've done is I've captured all of those in the Logic Analyzer, and I've done some analysis on the various signals and things. I'm just going to show you a summary of the logic analyzer traces, and then we'll go into some graphs and things that I've plotted to try and work out what was going on. So these are some screenshots of the traces that I've done, and really what I was looking for in the character mode test, we were looking for the color. So this basically is looking at the input to the video DAC, and we're looking for color 8, which basically is red on black background. And when I was looking at this, I was primarily looking at the video read-write signal, which is this one down here. But as I came to understand it more, then the Y0 signal here, which is when we're directly accessing the video RAM, was probably just as important, and in fact had a more correlation when we were getting the interference. So if we look at the next one here, this is just going down to the bottom. You can see here that this character latch signal, where we're loading the latches to do with the colors and the characters, then when the Y0 values there overlap with these, then that seems to be what's causing the issue here. And there are a variety of these signals. So this was a signal where the first update didn't result in any interference, but the second update over here did. And in this particular case, if we then look at where the Y0 signals are on the next slide, we can see that the Y0 and the character latch signals are actually sort of aligned in such that they don't really overlap. So as I was going through this, it became more and more apparent that it was the Y0 and the VRW signals I really needed to be focusing on. And this is another example where we have two updates, and again you get the two lots of red appearing side by side. And then down the bottom we can then again see that the Y0 is kind of overlapping with the character latch signals here. Then this was looking at graphics mode 2. So this was the white line appearing at the top of the screen and then reappearing all over the screen. I can see here that where we're actually writing to the video RAM here, we can see that we're doing this in sort of 8-bit bursts. And we can see here down the bottom we've got one video frame, so the vertical sync is going from here to here. So this is one 15 millisecond video frame. And then this was the line at the very beginning of the screen. So we can see here that we've got a period of 320 nanoseconds, which is one character wide, 8 bits wide, has got a white line there. And then further along, what we can see here is where we're getting the interference. And in fact, with the drawing the white line, because it reads the RAM first before setting the bits, then in fact we've got a read here where we're getting some interference. Then we've got the write here where we've got the Y0 signal and also the video read-write signal. And so what this indicates again is that these are the signals that we need to synchronize with the character latch values, and you can see down the bottom here this is where it's overlapping with the character latch. And another couple of examples here. So you get the gist of things, that really where these various timing signals, in particular the Y0 is overlapping with this character latch here, tends to be the thing that's driving the interference. And there are just various scenarios. So what I did from all this is I went through a load of the samples and I started to plot these out on some graph paper just to make life a bit easier. Just like to share with you now is some charts and things that I used to try and understand what was going on here. It's been driving me mad this over the last couple of weeks. But what this basically shows is the QA, QB, QC signals which are coming out of the video divider that produces the various clock signals. So the QC is in fact the CRTC character clock, and the character latch, which is the signal that actually causes the character and color attribute latches to load the data, and also the equivalent latches for the high resolution 2-color graphics. Then these are the signals that actually, from all the analysis of the logic analyzer output, that caused the interference. And what I did for a variety of the samples, I looked at where the Y0 video RAM select and the VRW video read write select were overlapping. Now in fact, as I went into it, it's more down to the RAM select, because we're both reading and writing to the RAM in some cases. And what I did is I plotted out where for instances where the snow was actually occurring. You can see here generally that these different periods are overlapping one or more of these periods of the character latch here, and then where we had circumstances where there were virtually no interference, then again these were largely occurring between the two character latch intervals. And down the bottom here is also doing some analysis of the CPU and clock signals. Now unfortunately these are now running at 8 megahertz, and so they do go in and out of phase of the clock up here, which is about 3.1 megahertz. The character clock here is about 3.1 megahertz. The dot clock is about 25 megahertz, and the period of this QA signal, which we're using for providing the timing of some of these things here, is 40 nanosecond width. So that's about 12.5 megahertz. Now, one of the things that we talked about earlier is the ability to stretch the CPU memory access, and what that works with the MRDY, memory ready signal. By making that signal low, what we can do is add an extra CPU clock or one or more CPU clocks onto the E signal, and what that also does is stretch the Q signal as well. And so what that might allow us to do is, in the circumstances where we have a situation where we're going to get this video snow, what we might be able to do is add extra CPU clock cycles to actually move the period where we're going to be accessing the video RAM to a period where we're not actually causing disturbance. Now at the moment, the Y0 signal is about a quarter of, so it's about 260 nanoseconds wide. When we had the 4 megahertz clock, it was close to about 500 nanoseconds wide. But now with this, the faster clock cycle, we can probably actually make this a little bit shorter. And certainly the video RAM that we're using has got like a 15 nanosecond access time. So the video RAM is certainly capable of working a lot faster. So what I played around with is a number of ways of looking at this. And what I've done is overlaid these on the various sort of stages. And the big issue really here is, depending on when the E clock cycle rises here, varies whether it hits the 0, 1, 2, 3, 4, 5, 6, 7 period. So depending on the relative phase of when the E clock goes high and which part of this cycle out, you'll get different interference according to it. And that's why it's taken quite some time to actually get to the bottom of it. This chart here as well just shows how, if we're adding various clock delays and things, then we can expand the period. So to cut a long story short, the analysis to work all this out, so all the logic analyzer signals are plotted there. It basically indicated that what we need to do is to make sure the Y0 and the video read write signals are within the two character latch values here. So there's a further analysis that I then did. So this was basically taking the E clock signal starting at from 0, 1, 2, 3, 4, 5, 6, 7, and then with actually counting these cycles all the way up to about 15, 16, 18. And what I was doing here really is to try and work out, is there a way how we can codify where we want these various signals to start. So what I've got here is the Y0 start, Y0 end, and when the video read write starts and video read write ends. And then if we need to include the memory ready signal to extend the clock. So where we have here the E signal, where there's dotted lines here, that means we've extended it by one cycle. And in fact, from the analysis I did on the previous sheet using these here, I was able to work out that I need to use one extra clock cycle if E started on 0, one clock cycle if it started on 1. I needed 0 if it started on 2, 3 or 4, and I needed 2 clock cycles if it started on 5 and 6, and only 1 clock cycle if it started on 7. So what I've then done down here is actually worked through all these various relative starting point of the E clock signal, starting on this point in the CRTC cycle. And what this has allowed me to do is to produce a sort of a table of the values relative to this starting point. And what it turns out to, this is a bit of a messy diagram, but it probably can indicate that what we've basically got for the various E starting points, there are three groups of data that basically we want to have memory ready starting on cycles 3 to 4, 3 to 7 not required, not requiring any delays, and then for the no delay, then we want the Y0 signal to start on the 3rd clock, end on the 6th, the video read write start on the 4th clock, end on the 5th, and then for these other two, 6 and 9, 7 and 8, 9 and 12, 10 and 11. So what this basically allows us to say is, relative to the starting point here, we can actually work out what the timings are for these various signals are relative to this thing across the top here. So what I'm going to do is, I've got these Atmel ATF 2500 PLD chips. So these are 40-pin chips with 48 flip-flops in them, so they're a lot more flexible than some of the other chips I've been using. And so if we just have a look at this, I think you can see, yeah, they're the 20 nanosecond versions of them. And so what I'm going to do is going to try and program these to allow for these different E signal phases based on the QA, QB, QC values, and obviously the offset that I've shown a little bit earlier to work out how to produce the Y0 memory ready and the video read write signals. So I should hopefully be able to get that done in the next video. So I'm going to break the video now as it's gone on a little while. So in the next video, what I'm going to be doing is modifying the circuit to put these PLDs in. And so if you don't want to miss out on the next video, please hit subscribe. And if you found the video useful, please hit like. Thanks for watching.